So for question number 1, we have a bit of a harder one. Now, I wouldn't expect this one to come up, but yeah, just in case it does. So, if you look at the basic one, there were 4 questions where they used 75% and 2 layers. So that's going to be what I expect to come up. This one is an advanced tutorial, so I'm just picking harder ones which are less likely to come up. Okay. So this time we have our first layer, which is 1 centimeter, and let's say we have 100% starting off, and once it goes through this layer, 25% has been absorbed. So there's now 75% that has gotten through or transmitted, and that means that so 25% of 100% was absorbed. Right. Now, the second layer, that's where it gets a little bit tricky. So we have our second layer, which is also 1 centimeter. And then when it goes through this layer, how much? So it's going to absorb 25% again, right? So it's going to absorb 25% of 75%, because that's how much is coming in. Now this is a bit of a harder calculation, so you need to find 25% of 75, so that's 0.25 times 75, which is equal to 18.75. Okay, so this has absorbed 18.75% of the total. And so then we started off with 75 and we've lost 18.75. So we have 56.25 getting through the second layer. So now we have 56.25%. And then, so we have the third layer. So that's, again, it's going to absorb 25% of the amount that comes in. So 25% of 56.25% will be absorbed. So you need to find 25% of 56.25. 0.25 times 56.25 is equal to 14. So 14% will be absorbed by the third centimeter. So we had 56.25 coming in, and we're going to lose 14. So that's going to be 42.2% that's getting through. Okay, so that's your answer. Option A. Now, yeah, that is a really hard one, so don't be too worried about that. The key thing, usually they're going to make each centimeter 50%. Okay, so that's what you should be focused on. But if that's easy for you and you want to get like really good grades, then you'd want to know how to do this as well. So potassium 40K has a half-life of 1.248 times 10 to the power of 9 years. A large rock currently contains 1 milligram of potassium. How much K would be left in the rock in 100 million years' time? So we have the half-life, which is equal to 1.248 times 10 to the 9 years. And we have the time. So time is 100 million years, so 100 times 10 to the power of 6 years. And we want to find out, and so the original mass was equal to 1 milligram. Okay, so we want to find out how much is left after time t. So the mass at time t is equal to the original mass times e to the power of negative decay constant times time. So remember that. So we're going to find out what the decay constant is. Decay constant is equal to 0.693 divided by the half-life. And remember that because we're going to use, because we have the time in years, we can also use the half-life in years as well. So that's 0.693 divided by our half-life in years, 1.248 times 10 to the power of 9. And that will be, where are we? 5.55 times 10 to the negative 10. So that's our decay constant. So that's original mass was 1 milligram times e to the power of negative decay constant 5.55 times 10 to the negative 10 times the time, which is 100 times 10 to the power of 6. And that will give you 0.946 milligrams. Okay, since we put in milligrams, we're going to get milligrams out. So 0.946 milligrams is equal to 946 micrograms. Okay, so if you wanted to go milligrams to micrograms, you just divide it by 10 to the negative 3. Oh no, sorry, yeah, divide by 10 to the negative 3. Okay, or you could times it by 1,000, same thing. Number 3, we have an old lab sample of radioactive cesium, which is labeled 5 millicuries. So that's your original activity. That's the activity at the time it was labeled. So that's 5 times 10 to the negative 3 curies. And you note that the sample is now 23.5 years old. So it's been 23.5 years. And you want to know what the number of disintegrations per second would be today. So that would be your activity. And remember that the number of disintegrations per second is in becquerels. So you want your activity to be in becquerels, which means that you need to convert your original activity into becquerels. So 5 times 10 to the negative 3 times 3.7 times 10 to the 10. So that's 1.85 times 10 to the power of 8 becquerels. Okay. And you have your half-life. T half is equal to 30.2 years. And because we have half-life and the time in years, we can just keep that consistent. So the equation is going to be A, the activity at time t, is equal to the original activity multiplied by e to the power of negative decay constant multiplied by time. So we need to find out what the decay constant is. Decay constant is equal to 0.693 divided by the half-life, which is 0.693 divided by 30.2, and that is 0.0229. So we've got a decay constant. Now we can put it all in. So original activity was 1.85 times 10 to the 8 becquerels times the Euler's number to the negative decay constant, which is 0.0229, multiplied by the time, which is 23.5. And that would give you 1.08 times 10 to the power of 8 becquerels. Okay. Sweet. Number 4, we have a radioactive sample which contains plutonium with an activity of 12 times 10 to the power of 16 becquerels. Given that the half-life is 4.96 hours, what mass of plutonium is present in the sample? So this one's a lot of steps. So the activity, so you've got the activity, and you can figure out what the decay constant is, and you want to find out the mass of plutonium. So we're going to use this equation. Activity is equal to the decay constant multiplied by the number of molecules. We know that the activity is equal to 12 times 10 to the power of 16 becquerels. We know that we can calculate the decay constant, so that's 0.693 divided by the half-life. And this time we want to turn that into seconds, so we need the half-life to be in seconds. So 4.96 times the number of seconds in 1 hour, which is 3,600, and that will give you 3.88 times 10 to the negative 5. So we have our decay constant using our half-life and our activity. So what we want to find is the number of molecules. Okay, so the number of molecules is equal to the activity divided by the decay constant, which is 12 times 10 to the power of 16 divided by 3.88 times 10 to the negative 5. And that will be 3.09 times 10 to the power of 21 molecules. So you've got your number of molecules. Next, you want to find out how many moles that's going to be. So 1 mole contains Avogadro's number of molecules, which is 6.02 times 10 to the 23. So n, little n, is the number of moles, is equal to the number of molecules, big N, divided by Avogadro's number. So that's 3.09 times 10 to the 21 divided by Avogadro's number, 6.02 times 10 to the 23. Where am I? 5.136 times 10 to the negative 3 moles. Okay, so that's the number of moles. Now you have the number of moles, so you can figure out the mass. So mass is equal to the number of moles multiplied by the molar mass. So 5.136 times 10 to the negative 3 times the top number, which is your mass number. So that's 243. So that's your molar mass. And that's going to be in grams. And that will be 1.25 grams. Okay. Number 5, we have a pure sample of silver, Ag, which has a half-life of 3.13 hours and an initial activity of 100 curies. What is the mass of the initial silver 112 sample? So if you want the mass, you're going to have to find the number of molecules. You've got the initial activity. So activity, and we need to have that in the correct units. So it has to be becquerels. So 100 curies has to be turned into becquerels, which is 3.7 times 10 to the 12 becquerels. Okay, so that's your activity. And the half-life. So if you have the half-life, you can calculate the decay constant. It's 0.693 divided by the half-life. 0.693 divided by 3.13. So that has to be in seconds. 3,600. So that's 6.15 times 10 to the negative 5. Okay, so that's, we've got the decay constant and our activity. So the number of molecules is equal to activity divided by the decay constant, just like last time. Activity is 3.7 times 10 to the 12. Decay constant is 6.15 times 10 to the negative 5. So that's 6.016 times 10 to the 16 molecules. So once we have the number of molecules, we want to find out the number of moles. That's the number of molecules divided by Avogadro's number. So 6.016 times 10 to the 16 divided by 6.02 times 10 to the 23. So 9.993 times 10 to the negative 8 moles. So that's the number of moles we've got. And then the mass can be calculated from the moles and the molar mass. So 9.993 times 10 to the negative 8 times your molar mass. What's that going to be? What's our molar mass? Yep, 112. So that's the top number. And that's 1.119 times 10 to the negative 5 grams. Okay, and you want that to be in micrograms. So divide that by 10 to the negative 6. And that will just be 11 micrograms. Okay. Whew. It's a lot of writing. Number 6 is continuing on from the same question stem. What will the activity of the sample be in 10 hours? And you want that to be in curies, so it's good to always check what units you want it in. So this time you want it to be in curies, and you had your initial activity in curies, so we can leave our initial activity in curies. So initial activity was 100 curies, and we want to find the activity at time t. The half-life is equal to 3.13 hours, and the time is equal to 10 hours. Okay, so this time we actually have the time and the half-life both in hours, so we don't have to convert the half-life into seconds when we calculate our decay constant. So 0.693 over the half-life, and we're just going to leave it in hours. 0.693 divided by 3.13, so that's oh, well, I did it a different way in my working. Sorry. Actually I turned, so this was 3.13 times 3,600. So I just turned them into seconds because I'd done that before, and we already have the decay constant from before. So in seconds, that was 6.15 times 10 to the negative 5. Remember? From our last question, from number 5. So that means that when we use our equation, activity at time t is equal to the original activity multiplied by the Euler's number to the power of negative decay constant times time. Because we use the half-life in seconds, we're going to have our time in seconds as well. So the original activity was 100, and the decay constant is 6.15 times 10 to the negative 5. And our time is 10 hours, so that has to be in seconds. So 10 times 3,600. And that's 10.9 curies. So yeah, what matters is that you have both your time, the t half and the t in the same units. Number 7, so you decide to build a X-ray source by accelerating electrons to a lead anode. What is the frequency of the characteristic K alpha radiation produced? You've got K alpha, so you can find the K alpha energy. So delta E of K alpha is equal to 10.2 EV Z minus 1 squared. So we're going to use the energy to find the frequency. So we need to have our energy in joules, which means that we're going to put in 1.6 times 10 to the negative 19. Z is equal to 82. So that's the number of protons. And that will give you 1.07 times 10 to the negative 14 joules. So that's your energy, your K alpha energy. And then energy is equal to Planck's constant times frequency, which means that frequency is equal to E divided by H. So that's 1.07 times 10 to the negative 14 divided by 6.63 times 10 to the negative 34. Which is 1.6 times 10 to the 19 hertz. Okay. Number 8, we have an X-ray tube which uses an operating voltage of 35 kilovolts. What's the momentum of the highest energy X-ray photons produced by this tube? So I'm just going to explain how a basic X-ray tube works. So you have your one side that is positive, and another side that is negative. Okay, and you're going to have electrons. So this electron it's going to be, so in this case we have if you have a positive plate and a negative plate, that's a potential difference, right? So in this case, our voltage is 35,000 volts on this side. And remember, the positive plate always has the higher potential. So going back to electricity, the negative plate has, we can assume, is 0 volts. Okay, and so this electron is going to be attracted to the positive plate and repelled by the negative plate. So it's going to gain kinetic energy, right? So it's going to gain kinetic energy. So it's going to gain kinetic energy, which will be equal to the electrical potential energy that it had when it was here. Okay, so that's so the change in kinetic energy is equal to the change in electrical energy, and the change in electrical energy is the charge multiplied by the change in voltage. Okay, so that's from electricity. When the electron hits this screen here, it's going to release a photon, and this photon is our X-ray. Okay, so the kinetic energy that our electron gained is equal to the change in electrical potential energy, and that is also equal to the energy of this photon. So that's also equal to the energy of the photon that's produced. And remember that if you have the energy of a photon, you can calculate the momentum, frequency, wavelength, and momentum, frequency, and wavelength as well. So on my cheat sheet, I just have a column for X-rays, and then what they're going to give you most commonly is just the voltage, so the change in voltage, and that's all they're going to give you. And then so all you need to recognize is that the charge, so in this case the voltage is 35,000 volts, and then the only thing that you need to realize that the charge, it's an electron, so we know what the charge is going to be. It's going to be the charge of an electron. Okay, so it's going to be the charge of an electron is negative 1.6 times 10 to the negative 19 coulombs. Okay, so you're looking for momentum, So on my cheat sheet, it's going to be like this. The QE times the voltage is equal to P times C. So you're just looking for momentum, so you're going to look for this equation, and then you want momentum on its own, so you're going to divide both sides by C, right? And that's going to be 1.6 times 10 to the negative 19 times 35 times 10 to the power of 3 divided by the speed of light, which is 3 times 10 to the 8. And that will be 1.9 times 10 to the negative 23 kilograms per meters per second. So whenever you have an X-ray tube and they talk about voltage, you're going to use these equations. So I'll just write them all down, but I have them on my cheat sheet anyway. But just so you guys know when to use them, so you have this one, the charge of an electron times voltage is equal to HF. So if you were wanting frequency, you would use this equation. If you wanted momentum, you'd use this equation. If you wanted the wavelength, it would be hc divided by wavelength. And if you wanted energy, it would just be that. Okay? So that's all on my cheat sheet. It's under the X-ray heading. Okay? So that's when you're going to use it, when they give you a voltage. And that's all they give you. Okay? And yeah, all you need to remember is that you know the charge, and it's going to be the charge of an electron. So number 9, an X-ray tube employs an accelerating voltage of 23 kilovolts. What's the frequency of the most energetic X-ray this tube can produce? So QE times V is equal to HF. F is equal to QE times V divided by H. So 1.6 times 10 to the negative 19 times the voltage, which is 23 kilovolts, divided by the Planck's constant, which is 6.63 times 10 to the negative 34. So that's 5.6 times 10 to the 18 hertz. Okay. Last page now. Number 10, we have a 10-gram tumor, which is irradiated with beta radiation. So this time they have given you the RBE. A total of 9 times 10 to the negative 2 joules is deposited into the tumor. What is the effective dose given to the tumor in rem? So we want the effective dose. So first of all, we're going to calculate the absorbed dose. The absorbed dose is equal to energy divided by mass. So our mass is, our energy is 9 times 10 to the negative 2. And our mass is going to be 10 grams. So that's 0.01 kilograms. So you want that to be in kilograms. So that's just 9 grays. Okay, so that's your absorbed dose. Now to find the effective dose, you're going to multiply your absorbed dose by the RBE. So that's 9 times 1.7, and that's 15.3 sieverts, and 1 sievert is equal to 100 rem. So you multiply that by 100, which will give you 1530 rem. Okay. And just while I'm here, 1 gray is equal to 100 rad. So I don't know why they do this. Like, it all seems pretty pointless to me having all these units. But that's just how it is. So sometimes they want rad, sometimes they want gray, sometimes they want rems or sieverts. So just know how to convert between them. Okay. All right. Number 11, we've got a 20-gram tumor irradiated with beta radiation, so that total of 0.05 joules of energy is deposited. What's the effective dose? So exactly the same. Absorbed dose is equal to E over M, which is 0.05, and the mass is 0.02 kilograms. So that's going to be 2.5 grays, and then your effective dose is equal to absorbed dose times RBE. So that's 2.5 times 1.7, which would be 4.25 sievert. And 1 sievert is equal to 100 rem, so you multiply that by 100, which gives you 425 rem. Okay. Number 12, we have a beam of gamma photons used in radiotherapy to irradiate a 50-gram tumor. If the beam has a power of, so remember power, it's very important that you know what power is, okay? So, and lots of people don't, okay? So power is equal to energy over time. So that's the number of the joules the number of joules that's used per second, okay? And the unit for that is watts, okay? So that's something that you always have to keep in mind, because it's going to come up in mechanics, thermo, electricity, and radiation, okay? So it's going to be a common theme across all of your modules. And so whenever you have a energy and a time component, you're going to think of power, okay? Yeah. So that means that we're getting 2.4 millijoules per second, and only 5% of the photons are absorbed. So we want to find out the effective dose equivalent over the course of 30-minute sessions. Now the units here are a little bit wrong, because for effective dose the unit is rem, not rad. Rad is for the absorbed dose. But it doesn't really matter, because in the end, because if you remember the RBE, so they haven't told you here, so the RBE of gamma is just equal to 1, so the absorbed dose, and if you multiply absorbed dose by 1, it's just the same as your effective dose and your absorbed dose. So what we're going to do is we're going to find out the energy that the tumor has received. So that's, remember that power is equal to energy divided by time. So energy is equal to power multiplied by time. So 2.4 times 10 to the negative 3 times the time, which is 30 minutes. So 30 times 60. And that will be 4.32 joules. Absorbed dose is equal to 4.32 divided by the mass. So 50 grams is equal to 0.05. Oops, so that's energy over mass. So 4.32 joules divided by 0.05 kilograms. And that will be 4. Oops, that's not right. Oh, sorry, I skipped a step. So they said that only 5% of the photons are absorbed. So only 5%. So the energy that's actually absorbed is equal to 0.05 times 4.32. Okay, so that's going to be 0.216 joules. So that's the amount that's actually absorbed. So absorbed dose is equal to 0.216 divided by 0.05. And that's going to be 4.32 grays. And then effective dose is equal to absorbed dose times the RBE. So that's 4.32, and the RBE is just 1, so that's 4.32 sieverts. And then to turn sieverts into rem, you just times it by 100. So that's 432 rem. Okay. So that's it. We do have a revision tutorial next week on Monday, I think. Yeah, Monday. Yeah. So I'll see you guys then. Yeah. And we'll just cover electricity, optics, and radiation again. Okay. All right. Thank you, guys. Good luck for cells and hubs.
Sorry, you can't tell.